The reduction of alkenes involves the addition of hydrogen and the conversion of this unsaturated molecule to a saturated molecule. A reduction process is exothermic and heat will be released in the process. One type of reduction is called heterogeneous catalytic hydrogenation. It involves the addition of the hydrogen molecule to the double bond in the presence of a metal catalyst such as nickel, palladium, or platinum. The metal catalysts are suspended in solution under a hydrogen atmosphere. For this type of reaction, hydrogen adds to the same side of the CC double bond. Hydrogen is adsorbed in the surface of the metal and interacts with the double bond at the same side to form this product. We can also have homogeneous catalytic hydrogenation. This is a hydrogenation process using Wilkinson's catalyst. It also involves syn addition of the hydrogen. As mentioned earlier, heat is released in a hydrogenation reaction, and this can be measured. The hydrogenation of 1-butene will give a delta H of negative 127 kilojoules per mole to form butane. If we are to consider the hydrogenation of these other isomers of 1-butene, here cis-2-butene and trans-2-butene, both of these compounds, upon hydrogenation, will also generate butane. It was measured that cis-2-butene gave 120 kilojoules per mole of heat, while trans-2-butene gave 115 kilojoules per mole. These heats of hydrogenation tells us about the stabilities of these compounds. If the heat of hydrogenation is lower, then such a compound must have lower energy or more stable. Comparing these three compounds, this double bond is monosubstituted, while these two double bonds are disubstituted. A generalization can be taken that the more alkyl groups attached or more substitution present in the double bond, the greater the alkene's stability. Also, cis-alkenes are considered to be less stable than trans-alkenes. Consequently, these isomers with double bonds that are disubstituted, trisubstituted, and tetrasubstituted are ordered in increasing stability. Now to oxidation. Oxidation involves the increase of oxidation number of the carbons in the alkene. Usually, oxidation involves the addition of an electronegative atom to the alkene double bond. The first type of oxidation is dihydroxylation. This involves cold dilute potassium permanganate followed by base hydrolysis to form syn 1,2-diols or glycols. Cold alkaline potassium permanganate is called Bayer's reagent. For this example, cold dilute potassium permanganate in the presence of sodium hydroxide will add 1,2-diols in a syn manner. Thus, the hydroxyl groups are cis. Another reagent that can also give the same product is osmium tetroxide. Osmium tetroxide in pyridine can form this cyclic structure, which is similar to the cyclic structure formed by potassium permanganate. Hydrolysis with sodium sulfite or sodium bisulfite can generate this syn diol. Dihydroxylation can also be facilitated by a reagent called MCPBA, or methachloroperoxybenzoic acid. MCPBA is a peroxy acid and can form a type of compound called an epoxide. Acid hydrolysis of this epoxide leads to trans-vicinal diols through anti-adhesion. In an acidic solution, the oxygen can abstract a proton from the hydronium ion to form this positively charged oxygen. You may notice the similarity between this species and this bromonium ion and mercurium ion. The presence of the positive charge on oxygen makes it more electronegative and allows it to pull electrons towards itself and bring a partial positive charge to this more substituted carbon. Hence, the nucleophilic water can attack at the opposite side of the epoxide and form this alcohol upon proton transfer. Ozonolysis involves the cleavage of the double bond. First, this reaction involves ozone at -78 degrees Celsius, followed by treatment with zinc in acetic acid or dimethyl sulfide. The result is the cleavage of the bond and the formation of aldehydes or ketones. Take note that in this reaction, this double bond is cleaved and an oxygen replaces the atom that is removed. For the case of this component here, the carbon in the double bond is replaced by the oxygen. For this case here, the bond is cleaved and this carbon is replaced by the oxygen. This is an aldehyde. The double bond O is at a terminal position, and this is a ketone. The double bond O is at a central carbon. In ozonolysis, an unsubstituted carbon forms formaldehyde. A monosubstituted carbon forms an aldehyde, such as this case. This carbon contains only one substitution. A disubstituted carbon forms a ketone, such as this one. It is an excellent means for locating the position of the CC double bond in alkenes. For example, this one. If this is a product of ozonolysis, can you determine the initial structure of this compound? Here you just need to look at the position of this double bond O and this double bond O. They are probably connected. And we can think of this going backwards, that this could likely be the starting material that produced this compound. If you cleave this bond, it will form a double bond O here. And cleavage of this bond will form a double bond O at this terminal position. If you count the number of carbons, they match right away. How about these compounds? What do you think is the starting compound? There are two formaldehydes here, and there are two double bond O's in this compound. These two formaldehydes may have been connected to these carbons in the starting material. And so if you think backwards again, this is likely the starting material before ozonolysis. If you cleave this bond, you will produce this part. If you cleave this bond, you will produce this part, and also two formaldehyde molecules. Potassium permanganate is a strong oxidizing agent, and with hot basic potassium permanganate, a different set of product is formed. Similar to ozonolysis, this double bond will be cleaved. For unsubstituted carbons, carbon dioxide will be formed. This carbon is unsubstituted, it will form carbon dioxide. Monosubstituted carbons form carboxylic acids, not shown here. Carboxylic acid has this structure. So you just replace R here with the alkyl group, substituting the double bond. A di-substituted carbon forms ketones. So here, this carbon is di-substituted and a ketone is formed. This reaction always involved potassium permanganate in the presence of a base plus heating, followed by an acid workup. Acid is added to the reaction to neutralize the basic solution. This can be a chemical test for alkenes because potassium permanganate is purple in color. This purple color disappears and forms brown MnO2 residue if an alkene or alkyne is present.